Okay, hello everyone. Welcome to another video that looks at the applications of differential calculus. And today we're going to be looking a bit more at motion, so we're going to be looking at instantaneous and average velocity and acceleration. So this is pretty fun because it incorporates a bit of physics, and it's also really good to get your head around some of the conceptual understanding of differential calculus through this particular application. Okay, so first off, what I've done, I've gone ahead and drawn on the board a displacement against time graph, an ST graph. And essentially, the first thing you should know is that the gradient at a given point on that particular function is the instantaneous velocity for that given time value. So say that was t equals 3, for example, and that would be instantaneous velocity, the gradient of the tangent to that point. Say we surveyed the average velocity between t3 and t5, then the rise over run is going to be the average velocity. The slope of that particular area, the slope of the chord between the two, would be the average velocity. So chord would probably look something like that, for example. So that's a really neat thing to know. If you get the gradient or the slope at a given point, depending on what you want for the velocity of a displacement graph, you're able to get the velocity. And it's the same sort of thing there. So with the velocity time graph, if we were to take the derivative at, say, time equals 3 as well, that gradient at that given point, the gradient of the tangent line, would be the instantaneous acceleration. And that's pretty cool to know as well. And similar concept again, if we have t3 to t5 on our velocity time graph, the rise and overrun, the slope of the chord in between those 2 points, would be the average velocity, the average acceleration, because we're going from velocity to acceleration. So if we were to look at this mathematically, essentially what we have is our s prime of t, so the gradient of our st graph there, because this is a displacement function, which is an st function, would be vt. So s prime of t, the derivative of our st graph or st function, is vt, the velocity function. And then the acceleration function would be the gradient or the first derivative of the velocity graph. And then because of that, our acceleration relative to our displacement time graph, the displacement time graph is the second derivative of the displacement time graph is acceleration. So if we go from here to here, that's first derivative. That's the first derivative of that. I mean, I know it isn't because I just draw two random st and vt graphs, but you get the idea. And then we have an at graph, which would be the second derivative of the original st displacement function. Okay, so hopefully that all makes sense to you so far. I've got the physics formulas up here to jog your memory. We have average velocity being displacement over time, and obviously we have displacement divided by time, rise over run for average velocity, and then we have instantaneous velocity again at that point. So it makes sense with the physics formula there. We have our rise over run for average velocity. Then for acceleration, it's known as delta v, or the change in velocity, over delta t, the change in time for acceleration. So if that's so, we can obviously see that we have vt, so we have the change in v, delta v, and delta t, and from that we're able to get rise over run. And be able to work out the acceleration for that using the concept of the slope of the tangent line. And then lastly, we have, obviously, we can rewrite that as Vf take Vi over delta t, because velocity final take velocity initial is just delta V as well. So that's how we link it all together. So now let's have a look at average velocity, and I've got the formulae ready to go up here, so we're able to follow along nice and easily. And average velocity, as I said before, we can see the average velocity is just displacement over time. So essentially what it's going to be is it's going to be y2 take y1 over x2 take x1. You all remember the slope formula for gradient. And that's essentially what we're doing here, except the notation will look a little different to that, because of course we're working with a actual function of st here, the displacement function. So what we have is we have the s of t, s of t2, take the s of t1, all over, and then we have t2 take t1. Okay, so essentially what we have there is we have the y value at the second time, so maybe the y value at 5, for example. Take the y value at 1, so it's the s of t, it's like the f of x. And then we have the x values subtracted from each other. So again, we're finding the difference, and that's essentially what it is here. Average, you can loosely translate to difference in quite a few different cases. So again, that's how it fits into our conceptual knowledge behind the mathematics. Now what about instantaneous velocity? That's at a single point. So we can't obviously, have those kind of values there. So that's when we actually look at instantaneous velocity using first principles. So the limit as h approaches 0 is equal to st plus h, take the s of t, all over h. And again, what we're doing here is we're simply making h incredibly small. So we put another point on our line, for example, say here, because we want to be able to survey the velocity there. And what we do is we just bring that point as close as possible to other points. So they're resting almost like literally on top of each other. H is approaching 0 in this case. So again, first principles concept, you probably should remember that from differential calculus before. So now we have average acceleration and instantaneous acceleration, and the good thing is they're not 4 different formulae, they're all very similar. Average goes with average and instantaneous goes with instantaneous. So what we get for the average acceleration is we get the velocity of t over 2, take the velocity t1, and that's all over t2 take t1. And hopefully that makes sense. You may remember when I explained it up there, again, it's just a concept of finding the chord and the gradient of the chord, because that would be the average. And then we have instantaneous velocity, and again, very similar approach. We use first principles, however we're referring to our velocity function, the v of t. And there we go, we have it. So we can find the average velocity, instantaneous velocity, average acceleration, and instantaneous acceleration. Now, sometimes with average velocity and average acceleration, you may need to use this formula, but without the limit as h approaches 0 there. Because what you may have is you may not have this actual value as being 5. It may be an unknown value, like h, for example. And h isn't approaching 0. H would be an actual value in that case, and you're finding the average velocity between that point. So that's where it gets a little confusing, but the best thing to remember is if you're looking at average velocity, then you don't have that limit as h approaches 0 there, because if you have h as an actual point, then there will be some h involved with the actual average velocity there, so your answer may have a h in it. Whereas the limit as h approaches 0 at your instantaneous velocity, you're only looking at it at one point, and h is becoming 0 or approaching 0, so therefore you won't have a h in your answer. So here it's okay to have a h, because sometimes you may be surveying a point that isn't numerical, whereas here you should get no h's in your final answer. And it's the same for the other two as well, because again, similar sort of concepts, it's just whether it's on a VT graph or an ST graph. If you're on ST graph, you're generally looking for the first derivative of ST, which is obviously going to be the velocity, either average or instantaneous. And then on a VT graph, you're going to be looking at acceleration most of the time. However, sometimes you may need to look at an ST graph and then be able to find the second derivative. But again, much less common, because generally you just need to find the first derivative. So there we go, we sort of established a difference between instantaneous and average velocity there, with the concept of the chord and the tangent, and mathematically again, some values may have h, some may not, but it's a great way to check whether you're on the right sort of process, because sometimes it's okay to have a h if you're doing average, and yeah, it's pretty good. So let's get into some actual conceptual questions and work through this process. I'll leave the formulae up on the board here, and hopefully you'll be able to apply them, use them, and feel relatively comfortable with them after a little while. And it's pretty good because physics is very interesting as well. So I've got a few things written down in the lower part of the board. So what I've got is the first problem, and there's going to be 6 questions, by the way, so hopefully by the end of this you understand the concept, and I've given you 6 good examples. But the first question is a 3-part question. That's where 3 of the questions are, and then I've got a second question that has 3 parts. But the first question says, a bus travels in a straight line based on the displacement formula, displacement function, and it gives us this. S of t equals t squared plus 6t take 3. And what it tells us to do is the first thing, and t is greater than or equal to 0, and it's in meters and seconds. So it gives us a function, and it tells us that t is greater than 0, and the units that we're working with are meters and seconds. So the first part of the question, I know I've said that twice now, but what would t less than 0 mean? So in here we have it is greater than or equal to 0, but what would it mean if t was less than 0? And maybe you might get a question like this one day. But I'll explain it nonetheless. So we have our origin, and we have the bus. I believe I used an example. Yes, that's right, I used a bus. Yep, brilliant drawing there. But the bus is going to a certain point on the st function, and it's obviously moving in the positive direction because t is greater than 0, so it's moving to the right. Now, if t was less than 0, then it means it would be going the other way. And you're probably thinking, well, how can that be the case? I mean, it's still moving, it's still actually got some distance there. And the thing is, we're looking at a displacement time graph rather than a distance travelled time graph. Because if we look at our displacement, we know that the difference between displacement and distance travelled is that displacement is a vector quantity. And that means that it needs to have both direction and magnitude. So because displacement is a vector quantity, t less than 0 means that we would be moving to the left from the origin in the other direction. But in this case, it says that t is greater than or equal to 0 for any path of the bus, so therefore our st graph only exists in this quadrant up there. Or technically, it could exist down there if we had a negative velocity, or negative displacement, which we couldn't technically have. If this was a VT graph, then we could have that. But anyway, there's the first question sort of answered. What does the t greater than 0 mean? And the answer is it's there because of its displacement being a vector quantity. Displacement is a vector quantity. So, now that we've moved on from that and we've established that, that's our first question done. Let's move on to the second question, and we need to find the average velocity. So I'll just write this up here. So looking at average velocity, so of course we're going to be looking at our first formula, and it's the average velocity from t equals 3 to t equals 9. So it's given us a specific range, and it wants us to be able to find the average. So again, we'd have our st graph there, and you can see that it's obviously going to have a curve up there because it's going to be a quadratic of some sort. So it's always good to have that visual there. I know that that's not going to be the actual graph, of course, but we just have that there just to sort of get an understanding of it. And what we're doing is we're surveying t equals 3. What's the gradient there and at there? And joining the actual points to form a tangent or a chord. Okay, so with t equals 3, we can go into and use this formula. So we have our s of t. So it will be essentially putting in 9 everywhere we see t there. So it would be, and we write this as being the average, or we can also write it as the s prime of t, because that's what we're working out. Again, the first derivative of displacement is velocity. And we have 9 going into there, so that's 81 plus 6 lots of 9 take 3, all as one function, so we need to put brackets around it. And then we need to do the st of 1. So time 1, time 1's 3, so again, we simply substitute it in. 3 squared plus 6 lots of 3 take 3. And that's quite wonky, but that's all good. And then that's all over 9 take 3. So again, we're just putting it into slope form, so we're just finding that chord between the two values. Then we need to find our s prime of t, and to do that, what we can do is we can do the arithmetic there, which would be 81 plus 54 take 3, and if you're like me and you just want to double check to make sure you're not making any silly mistakes, then you can use your calculator to be able to do so, and you should get 132. So we have 132, and then we subtract, and then we work out the next bit. 3 to the power of 2 is 9, plus 6 lots of 3, so that's 9 plus 18, which is going to be 27, and then we take 3, so that's going to be 24. All over 9 take 3, and therefore our s prime of t, and we can work that out. First off, we just do the numerator, so we have 132 take 24, and that gives us 108 over, and then 9 take 3 is 6, so our s prime of t is going to be equal to, and 108 divided by 6 is obviously 18, so therefore it's in meters per second. Always remember units, especially in physics here. So that would be our velocity based on the displacement function. It's the slope of the tangent there between those 2 points. Or the slope of the chord, I should say. But there you go. You've got an understanding of how to be able to work out average velocity now between 2 different t values. So let's make things slightly more complicated and move on to the next question. So this is question 3. And I'll just erase that. Okay, and question 3 states t is equal to 3 and another t, t1, so we have t1 and t2, is equal to 3 plus h, and we need to find the average velocity. Okay, so now essentially what we're doing is we're doing the same thing as here. We're just plugging it into this formula here, but just remember we don't have the limit as h approaches 0 out the front. H is an actual numerical value, or a constant that we don't know in this case. It's not trying to get it as close as we possibly can. H is a value on the actual graph. So if I were to draw this, again, it's not going to be an accurate representation of this particular displacement function, but it gives the idea. We're going to have 3, and then somewhere, we don't know where, we're going to have h, and we're working out the slope between them. So the velocity, the average velocity between those 2 different times. Okay, so let's work this out. So we have our s prime of t, which equals our v average, which equals in turn, and what we do is we simply substitute in 3 plus h wherever we see t, so it's 3 plus h squared plus 6 lots of 3 plus h take 3, and I'm probably going to go around to the other side of the board because I'm starting to get a little bit wonky. And oops, there we go. I'll just erase that and rewrite that. What we have is we have 3 plus h and plus, I'll just get into here so I don't shadow the board out, and from that we have 6 3 plus h take 3, and on the end here we simply have that in brackets, and it's subtract, and then we have 3 squared, and then plus 18, which should be take 18, because we have take 18 there, because negative there and another positive there makes it negative overall, take 3. And that's all over, obviously, just h. And the way I get that is, remember, it's going to be 3 plus h take 3, because that's going to be our t2 value there, and that's our t1 value there. Well, those two cancel out, so it's all over h. Okay, so now our v of t, our velocity function based on the average velocity there, is going to equal 3, and then we go 3 squared, and then we have 2 lots of 3h, so that makes 6h. Plus h squared, and then it's plus 18, and then we have plus 6h, then take 3, and then take 9, and then take 18, take 3. So okay, what can we actually cancel out? We can cancel out the 3's, and that's technically plus 3 there. Sorry, it's getting a little bit crowded, but we can cross that out, and we can cross out 3 squared and 9, because 3 squared and 9 are the same thing, and we can cross out the 18's as well. So that's good, and we're left with, and I'll probably go to the other side of the board again. Sorry I'm swapping around, and sorry there's a bit of shadow, but hopefully you'll be able to learn from this, so it's not too bad. And we end up with h out the front, 6 plus h, and then we also have plus 6, all over h, and then we can cross them out. So what I've done there is I've just taken all the h values from what is remaining, and then I've just put them out the front of the equation, and I filled in the rest of the bracket as is. And then our vt function, which of course is the s prime of t, is going to equal 6 plus h plus 6, which is going to be 12 plus h meters per second. And again, h is an actual value of time there, so it's not the limit as h approaches 0. So when you've cancelled out the denominator by just isolating h as a common factor, this h actually gets to live in this particular scenario. We don't kill it because we're not approaching 0. So, let's move on from that and get on to our fourth question. And our fourth question is about a train this time. It's a similar sort of concept, but a different form of transport. And I don't think we're going to be looking at displacement anymore either. So what we have now is we have a question that says, find the value of the s of... Oh yeah, we're still looking at it, sorry. We're still looking at displacement, so I'll write that function back up again. Sorry about that. I was one step in front of myself today. But I guess that happens from time to time. And of course, t is greater than or equal to 0. But this time we're going to be looking at instantaneous velocity. And I probably shouldn't have said that because the actual question itself says find the value of the limit as h approaches 0 of the s of 2 plus h, take the s of 2 over h and interpret its meaning. I've just sort of spoilt its meaning, but I'll show you how I actually understood what its meaning was from there. So what we have is we have the limit as h approaches 0, and we have the s of 2 plus h, take the s of 2 all over h, and we're going to be looking obviously at a point 2, for example, and because there's a limit as h approaches 0 there, it's instantaneous velocity, because again, on a graph, we're making h as small as possible, so we just get the equation of the tangent, so what the velocity is at a given time value. In this case, time equals 2. So what we do is we simply substitute in 2 plus h wherever there's a t there, so we get the limit as h approaches 0 for 2 plus h squared plus 6 lots of 2 plus h, take 3, and then all of that in brackets, and then we take, and from that we have the s of 2, so it's 2 squared, take 2 squared, and then we can, because that's a positive there, it's going to be negative here because there's a negative in the middle there. I could put it in brackets, but I'm just going to leave it out, so it's going to be negative now. So that's going to be take 12, because 2 times 6 is 12, take 3. And then that's all over h. So what we do is we have the limit as h approaches 0, and we expand out the bracket, so we get 2 squared, and then we need 2 lots of, and then it's 2h, so that makes 4h. And then from there we actually have plus h squared, and then plus 12, and again just using the distributive law there, plus 6h, and then take 3, and then take 4, take 12, and then that last one should be plus 3. So cancel out the 2 3's there, just because we can cancel them out, and we can cancel out 4 and 2 squared, and we can cancel out the 12. So what we're left with is we're left with all the values left with h, so we know we've done it correctly because it is a first principles concept. Then we write h out the front, so we cross that one out, and we have 4 there, and we cross one of them out, so it's just plus h there, and then we have plus 6h, so it's just plus 6, because the h has gone out the front as a common term between all the remaining terms, and that's all over h, so we cross them out, and from that, it's the limit as h approaches 0, so we can get rid of h, and we get our velocity function as being 10 meters per second. And that 10 meters per second is the v of 2, or the s prime of 2, because we're surveying instantaneous velocity at a point, at time equals 2. Okay, so now, last 2 questions, and hopefully this isn't going on too long, hopefully it isn't boring you too much, hopefully a lot of it is new content, but we've looked at the first 2, so we may as well just apply the next thing to the last 2 as well, and let's have a look at average acceleration. So with this question we're looking at the train finally. Sorry I kind of messed it up before, but we've got our velocity function here, and what we're doing is we're looking at a train that is going in a straight line. We're looking at one-dimensional kinematics here, so we're looking at one-dimensional motion, and it's going on a straight line with the velocity function 4t, plus 6, sorry, 4t plus 6, and the values are meters and seconds for the corresponding scale, because sometimes you may have centimeter seconds, although meters per second is the SI unit for that. And from velocity we want to be able to find the acceleration, and we need to find the instantaneous acceleration at t equals 5. Okay, so instantaneous acceleration, we're going to be looking at the last formula, so we're going to be applying first principles again, and from that we have the limit as h approaches 0 for the v of t plus h, because we're looking at our velocity function, and we're adding h, which is going to become infinitesimally small because of the h approaching 0, and then we subtract the v of t from that, and it's all over h again. It's on the board as well, so what more could you ask for? The limit as h approaches 0, and again we just put in t plus h wherever there is a t in the original function for this part, because again it's just like having the f of x plus h in your first principles. So we get 4 lots of t plus h plus 6, and then that, and we subtract the velocity there, and the velocity is obviously just 4t, and it will be take 6 because we have a positive there, but we have a negative before it. And that's all over h, and therefore we take the limit as h approaches 0, and it becomes 4t plus 4h plus 6. Take 4t, take 6, and we cross out the 6 terms, cross out the 4t terms, and it's all over h, and therefore the limit as h approaches 0 is going to be h lots of 4, again I'm just moving that h out the front, over h, so therefore instantaneous velocity, or should I say instantaneous acceleration, sorry, the I'll write it as v prime t, which is essentially the derivative of the velocity function, but it'll be obviously the a of t now as well, and that will be 4 meters per second squared. So on our graph, when we have the value for instantaneous velocity at t equals, oh, I did t equals 4, didn't I? Oh, I did instantaneous velocity just for the general function. Yeah, but from that you can see that obviously it's just gone ahead and I've worked out the instantaneous velocity of the actual function itself. So now from that, sorry about that, I confused myself there, but we're looking for the actual acceleration at t equals 5, and again it'll be 4 meters per second squared, because obviously this is a linear equation here, so for any values of t it's going to be a constant acceleration, because our velocity is constant, so our acceleration is going to be constant too. Okay, so that's why we got that result. You could actually put in 5 plus h in there, and that's probably what I should have done to make things easier, but I guess plugging it in at the end does help. It's just the fact that you obviously don't have an x there, because again, constant slope means constant acceleration, means that anywhere on this velocity function, the instantaneous acceleration is going to be 4 meters per second. And that also answers the next question as well, which is question 6, which just sort of says, what would the time be between 2 and 7? The average velocity, and the average velocity, because of that, is obviously going to be, average acceleration, sorry, what would the average acceleration be? So, average accel would be equal to 4 meters per second squared for the last question, because of course it's a linear trend and we're just surveying it between 2 and 4, both of which is 4. So if I were to write this out, and it would be the vt2 take the velocity function at time 1 all over h, t2 take t1, because we're looking at average accel, not instantaneous. And from that it would just be, what we do is we simply substitute in the values. So in fact I'll do it now from our original function. So it was vt equals, and it was 4t plus 6. So again, that's 4 lots of t, so that's 4 lot of them. We want to survey it at 7, so that's 28 plus 6, which is going to be 34. 34 take, and we're looking at time 2, so that would be 4 lots of 2 plus that, so that would be 14, and that would be over, and we do 7 take 2, so that equals 20 over 5 equals 4 meters per second squared, so that would be the average acceleration between those 2 points, because we have a linear velocity time function. Hopefully this was okay. Hopefully I didn't lose it too bad towards the end with a few little mistakes there, but again it was a 30-minute video. But hopefully you understand it. It's a really good application, differential calculus, to get your head around. Hopefully your conceptual stuff at the beginning is still sticking in with you, where you're looking at average and instantaneous and the difference between them. But that is an application of differential calculus. It's quite fun if you like physics and maths like me. So there it is, and looking forward to more future videos as well.